So, ladies and gentlemen, today we're going to talk about what I think is a pretty easy topic. It's a really easy thing, but it's really important that you understand what's going on. Okay? Because this topic, it kind of sets up how you solve any type of problem that has to do with when we get to Newton's second law. Okay? So today we're going to talk about this thing. I don't want green. They're called free body diagrams. Okay, so we're going to talk about free body diagrams today, and again, they're really easy, but you have to know them, and you have to know how to do them really well. Okay? So a free body diagram is just a picture that shows all the forces acting on an object. Okay? So it's just a picture that we draw that shows every single force that pushes on an object. Okay? Pushes or pulls. It's that simple. Kind of crazy, huh? So we don't draw them, though, in terms of like, oh, look, if I have a car, let me draw a car. Right? If I have a guitar, let me draw the guitar. Right? It doesn't work that way. All you do, and it's really simple, is you just draw a dot, and that represents the center of mass of the object. All right, so when we deal with forces, we pretend that all the forces acting on the object are acting on their center of mass. All right, and then the center of mass is where we can pretend that all the mass of the object is located at. Okay, so we just start with a dot, and that's going to be our object. All right, the first force that we can look at, and every object should have, it needs to have, is weight. Okay, now weight always goes straight down. Okay, so weight is a force because of an object's mass. All right, so if you have mass, you have weight. Okay, you have to have it. Every object that we could potentially apply a force to has to have weight. Even if we're talking about like a particle of air, it has a mass, so it has a weight. Weight itself, if I want to know how much an object weighs, it's just mass times gravity. Okay? So what is weight dependent on? Okay, so what do you think weight is dependent on? The mass and what else? Gravity. Okay. So this brings an interesting conversation. Anthony.
Yeah.
What happens to your weight if you go to the moon?
It's less. Well,
Why?
My weight isn't less.
Your weight's not less.
The gravity, the mass.
Your mass is less. Okay.
Ooh, I just stumped you.
You did?
A little bit.
You sure you stumped me?
Pretty sure.
All right, so we think back to chemistry. What is mass? What is mass?
How much space you take up? Yeah.
That's volume. The amount of space you take up is volume. What is mass? What do you think? What is mass?
That was one.
Nobody remembers? This is like chapter 2 in chemistry, mass.
Yeah, it was. You're speaking like a year ago.
So, mass is the amount of matter that makes up an object, right? It's the amount of stuff that makes up an object. If I send you to the moon, does the amount of stuff that makes you up change?
No.
Okay. So what changes?
The moon, like the size of the lawn.
Gravity changes on the moon, right? Okay, so when you go to the moon, the gravity acting on you changes, right?
Right.
Okay? Actually, on the moon, it's actually 1/6 of Earth. So what changes when you go to the moon?
There's less forces. Your inertia.
No, your inertia doesn't change because that has to do with your mass.
The gravitational pull is.
All right, so there's less gravity, so does your mass or your weight change?
No, just the gravity does.
Your weight changes. Your weight has to change because if your gravity changes,
Alright.
your weight has to change with it, right? Okay?
You stumped me.
So, no matter where you go, your mass will always be the same, right? If I ship you to Jupiter, if you have a mass of 75 kilograms, you still have a mass of 75 kilograms on Jupiter. But you're about 3 times heavier on Jupiter, 3.5 times heavier on Jupiter because gravity is 3.5 times greater. Okay? So weight is gravity dependent. Okay? So depending on where you go, your weight changes with gravity. Right? They say when you go into space, you're weightless. You're weightless because there's no gravity. But you're not massless. You still have mass. Yep.
Why, when you're in the pool, you're lighter?
You feel lighter because the water is doing a little bit of holding you up. Okay? It's called the buoyant force. Okay? So in space, again, you may be weightless because gravity is very, very small, but you still have mass. You are not massless. You still have stuff that makes you up. Okay? So you've got weight. That's the first thing you should always draw, right? Weight's easy, straight down. Let's say we're talking about a book on a table. Right? Book is just hanging out on a table. Okay? What other forces do you think are acting on the book?
Gravity.
Well, we've got weight, so that's gravity, right? So when we say gravity, we're talking the weight. Okay? What else is, like Brian's folder right here? What do you think is also applying a force on his book? Table, right? The table's pushing up on it. Okay? So the okay. This force that's pushing it up, we call the normal force. Now the normal force, we call it the supporting force. That's a force that holds things up so that you don't fall through. Okay? So there's a normal force acting on you right now from the chair. Right? All your weight is going straight down. The chair is the normal force that is supporting you going up, pushing up. Okay? So in the case of this book, right? In the case of this book, how can we relate the normal force to the weight?
It stops it.
Well, let's say they're numbers. How can we relate these two?
Equal.
How do you know they're equal?
Because if, say, gravity was more, then the book would go through the table.
All right, so kind of. So Anthony said that, ladies, Anthony said that these two are equal to each other, right? Which is true. But the reason why we know that they're equal to each other in case of this book, because it's not moving, right? We just talked about a couple minutes ago the fact that if you have a force, right? If you have a force acting on an object, you're causing its speed to change. Well, this object's speed is not changing, so there has to be no force acting on it. Okay? Does that make sense? Okay. Now, normal force has to do with something underneath it pushing up, the ground, a table, a chair, something like that. But there are other ways that we can get this force and not call it the normal force. Okay. Another common force you might see is called tension. Okay? So if you're pulling on something with a rope or a chain, we call that tension. They're all forces. These are all forces. We just give them specific names. Okay? Does that make sense? That make sense? Right? And another force we might see is friction.
Wait, so force in a rope, would that be like tug of war?
Tug of war is a perfect example of tension. Yep.
That's what I was wondering.
Yep. So again, friction, there's a couple things about friction. Friction is the interaction between two surfaces. If you were able to get a really good microscope and zoom in on, like this book, you would see that the surface is not nice and smooth. It's very jagged. Same thing for this table. Friction occurs when those jagged edges, they lock in to each other. When they slide across each other, they lock in kind of like Velcro. Okay? And they hook in, and that's what, it's kind of like a resistance. Typically, friction opposes the direction of motion. So if your object is being pulled to the right, friction is going to travel to the left. Okay? Friction is a force that tries to slow you down. Think of it that way. Okay? Friction, I write, is kind of like this curly F. If I want to know how much friction is, it's this thing called mu times the normal force. Now, mu is the coefficient of friction. Okay?
So that F is the friction.
Yes. This is not an M. This is the Greek letter mu. Okay? And yes, you have to make it like this because of it's really just like a script U. Okay? A coefficient of friction, all right, is a number that tells you, it gives you an idea how much friction is going to occur. Okay? A low number, so a number like close to 0.1, 0.2, 0.3, all right? That number of coefficient of friction means it's very slippery. Okay? A higher number, closer to 1, for 98% of everything in the world, you're not going to have a coefficient of friction greater than 1. 1 is typically the highest number you can get. Okay? So the closer you are to 1, the greater the friction. Okay? And it's dependent on your materials. So there are people in labs who literally just take different materials, slide them across them each other, and figure out what that coefficient of friction is so that you can look it up in a book, in a chart. So typically, if I say the coefficient of friction is 0.2, you just plug that in for mu right here. Okay?
What is N?
N is the normal force.
Would there be a number for that?
You may have to find it. And we're going to talk about how you find that and all that, okay? Yep.
I'm like the same for everyone.
No. No. All right, so, give you an idea about coefficient of friction. Rubber on pavement is about 1. The coefficient of friction for, like, your tires of your car on the road is 1. As soon as the road gets wet, your coefficient of friction goes down to about 0.3. Right? So it goes from really good surface, right, lots of traction, to quite slippery. Okay? So that if you're going on like curves and on on-ramps and on exits for highways, right, you notice how sometimes the speed limit may be like 25. Right? That's typically a speed that engineers have determined is pretty much the maximum when it's rainy or icy out, that you can go around that turn. Okay? Does that make sense? Like they've done the calculations, you can do the calculations to find when do you lose traction, all right? And then you're able to find out at what speed, and that's typically, it's probably, faster than the speed limit, but they want the speed limit obviously to be below that so there's no cars going all over the place when it rains. Okay? So there's a scientific reason why speed limits are set on on-ramps and exits. Okay? On the highway, that's a different story. Okay? So lastly, let's say we take this book, right, and we hook up a string to it, and I start to pull the book along the table. Okay? If I do that and I pull it to the right, I get that tension. Okay? But there's also friction between the book and the table. How do I show that there's friction? Going the other way? Okay. Now, here's another thing we can throw in there. So we know that tension is going to go this way because tension opposes the direction of motion. Let's say I am pulling it at a constant speed. So I'm pulling the book at the same speed the whole way. how do I show the friction, or what happens to the friction in this diagram, do you think?
It's equal,
What's equal?
that tension.
So how do I show it here?
Yeah, like the
Same length, right. So if it's the same, if the friction cancels out the tension, then they need to be the same lengths. If it's moving at constant velocity.
Yeah.
If the book is moving at constant velocity. So if this just slides across at the same exact speed, right? Whatever force I'm pulling it with, friction's doing the exact amount in the opposite direction. So that when I add these two together, they're equal to 0. Okay? So the last big thing, and this is really important, we get this thing called net force. Okay? And net force is a sum of all the forces acting on an object. So if we added up all these forces, we'd be looking at the net force. And net force is really the important thing when it comes to how an object's velocity or how its motion is changing. All right? We look at the net force, not the individual forces, because these are going to do things to each other, right? That's going to change the amount of force that the book experiences. Okay? Does that make sense? So when we're talking net force, I'm talking a sum of all the forces acting on it. Okay? Are we good?
Can you re-explain that?
Net force?
Yeah, the sum.
Okay. So I want to know how much force that book really experiences. Right? So I would take this force and add it to this force. But because they're equal amounts, but in opposite directions, the net force in the x direction would be 0. Same thing here. The normal force is the same as the weight. So when you add them, they cancel. So the net force in the y direction is also 0.
Will they have numbers so that
They can. Shh.
because like how could you tell if like maybe that side's like a little bit long?
You'd make it obvious. So if this tension was greater than the friction, you'd either make the tension really long or longer, or you'd make the friction shorter. It would be obvious. Or you just label on here like tension equals 5, friction equals 4. Okay?
If they don't cancel out.
Then we know that it accelerates in the direction of the greater force. Okay? That's a good question.
Cool.
Yep, Alyssa?
Is that how you start geeking out?
All 4 together? You would only deal with the x and with the y. Because remember, x and y are independent. Okay? Good, yeah, so that's a good question. What happens if the tension is greater than the friction? Then the object book is going to accelerate in the direction of the greater force. Right? So if the tension is 5 and the friction is 4, the net force is 1. And it's pointing to the right. So in that case, the book is going to accelerate to the right. No? Maybe. Anybody know the units for force? So kilogram meters per second squared is good. That's true. We can call it the kilogram meter per second squared, but there's something easier. No. Good idea, though. So we call it the Newton. Capital N, the Newton. Okay. So we call it the Newton. Think about, if you can't come up with the unit, think of cookies. All right, the Fig Newton.
Is it capital every time?
It's capital N, yeah. Okay.
What is that?
I wouldn't call it I would call it
Kilogram meters per second squared.
What are they called?
Okay.